Thank you so much. Thank you so much for giving me this opportunity to be here. And yeah, it will not be really a talk about quantum, but I have a few quantum things at the end. So today I'm going to talk about gravitational wave astrophysics in general. I will talk about the tools that we use for observing the sky. I will give some introduction to so-called core collapse supernova, and I will give an announcement about the symposium that I'm organizing this July, and then a little bit of future directions that I'm interested in that involve actually a certain quantum framework. So let's start from general introduction. So gravitational waves discovery was like a big discovery that basically changed our understanding. Like with every detection, we are learning more and more about the universe. And I like to show this graph, basically highlighting like different fields that they were getting Nobel prizes over the last century. And if you think about astronomy, astrophysics, about the Nobel prizes that were given to for like theoretical or using the gravitational astronomical data, the number of them is increasing. So this is something to note. Like in the last decade, we had actually like 7 Nobel prizes. 4 of them were directly linked with general relativity, so discover gravitational waves, cosmology, and finding supermassive black hole in our galaxy. Black holes are a consequence of GR. And then there was 3 of them that were using astronomical data, the expansion of the universe, neutrino oscillations, discovery of exoplanets. So overall, with bigger and bigger surveys, with more and more advanced detectors to observe the sky, is actually worth noting that going into astronomy and astrophysics may be really, really promising. And especially gravitational waves are probing stuff that we couldn't probe before. So in Poland, we have a group of like 20, 30 people working on gravitational waves directly, and this is called Polgraf. And Polgraf was the founding member of the Virgo collaboration. Now this is the founding member of Einstein Telescope collaboration. Some of the example achievements from the group is the correct prediction of what LIGO has seen like as first. There was a lot of debates. Do we discover first core collapse supernova? Do we discover continuous waves from a rotating pulsar? Do we discover binary neutron stars? But at the end, it was black holes, like that were pretty heavy, and the Polish group detected it, predicted it correctly. Also, the prediction that we'll detect very heavy black holes above 100 solar masses. Mathematical foundation for searching for continuous gravitational waves. I should have put here that yeah, the proof that gravitational waves are real and they carry energy is actually coming from here. It was made in the 50s, 60s by Professor Andrzej Trautmann. And we had, it's a pretty active group. It's a small but pretty active group. We had LIGO Virgo Kagra meetings. A few months ago, we had the 3rd annual meeting of the Einstein Telescope collaboration. And I will talk about Einstein Telescope just in a moment. I'm organizing the LIGO Virgo Kagra symposium on core collapse supernovae, and I will also tell it a little bit later. And we'll also have the LIGO Virgo collaboration meeting in like a year or 2. So it's there's a lot of activities, and I'm really happy that I came here to this group, and actually that I came back to Poland too. So how to generate gravitational waves? If you want to create gravitational waves, you need to have so-called a spherical mass energy movement, the quadruple emission. So if you think about a star, a neutron star, a pulsar that is spherically symmetric, like ideally, and it's like rotating even fast, we don't have emission of gravitational waves. We need some deformation, like a mountain, like a deformation of the surface. Then we have a generation of gravitational waves. And you can imagine that to break, say, spherical symmetry, if we have two black holes, these are practically the most efficient generators of gravitational waves. And there are many sources of gravitational waves, and I divided them roughly into like standard. So stellar mass black holes, this is what we are detecting, like basically regular. We had around like 300 of them now. So during the first observing run, when we have detection of gravitational waves, it's like we say like, oh wow, another black hole, like the second or third one. But now it's like we see, oh, binary black hole, like vanilla, like okay, yeah, let's move on. And then we have, I call them exceptional gravitational wave sources, and I will explain that like a little bit later. So just a very brief overview to gravitational wave interferometry. So we use gravitational wave detectors. Our gravitational wave detectors are interferometers that are of a large scale. So we have the interferometers with the arms of 4 kilometers in LIGO, 3 kilometers in Virgo, and in Japanese Kagra. And if you probably are very familiar with interferometry, but just as a quick overview, we start from a laser source. We have a beam splitter that splits the light into two beams. The beams are they're traveling to the test masses at the end of the interferometers, at the end of the arms, in one direction, in the other direction, and then they go back, and then they recombine again in the beam splitter. They go to the photodetector, and photodetector is by default kept in like a dark mode. So it's easier to detect light when it's dark than detect light when it's like bright. So they are kept in the destructive interference. And if the arms, the length of the arms are changing, then we have this is a signature of having gravitational waves, and we basically measure the difference of these arms that is proportional to this h of t, our strain, gravitational wave strain. And they have to be, these are very, very sensitive instruments, and they have to be far away from all the noise disturbances. Here I show the detector that is in LIGO Hanford on a desert in the Washington state, and I was there for like half a year as a fellow. Yeah, it's coming. As a fellow, and I'm actually one of the few people who are allowed to actually go inside the vacuum chambers for like certain work. It's a very, very clean environment. So yeah, you can see me right next to the beautiful like mirror at the end station, and it's me smiling. Yeah, there's as I said, there's a lot of noises, and I like to show this one that yeah, you never know what can come to your detector. And it was not me. It was not me. So we are currently in the fourth observing run of LIGO Virgo Kagra. During the first observing run, we have detected gravitational waves, and this is the time when I started roughly my PhD. So it's like, yes, my PhD makes now so much sense, like the discovery. Then we have discovered like several sources. The biggest discovery of the second observing run is binary neutron star. Then during the third observing run, the biggest thing was intermediate mass black hole. So the black hole that ended up to be 150 solar masses. At the moment we are doing, at the third observing run, we had a special paper with the supernova that exploded like outside of our galaxy, but we had we got some special interesting results. We had so far 201 detections, and we divided it into the O4A, O4B, and O4C. And at the moment we are in the O4C stage, but the detectors are off for 2 months because there's like some piece of hardware, some valve to the vacuum chamber that is like faulty, and they have to basically repair it before the hurricane season in Louisiana. So it's usually like summer when the hurricanes basically are hitting like all the south of United States, and it's better to fix it. Vacuum chambers are the most critical pieces of infrastructure. If they break, the experiment will be over. Like it's not possible. You have to basically replace everything, which is like extremely costly. So yeah, like all this vacuum stuff is critical for the operation. And yeah.
Can I ask a question?
Yes, yes.
So in the current American political climate, do you see any problems with future funding of LIGO? It is funded by NSF.
Mm-hmm. So I would say, yeah, I don't have. It's in a sense that you have a glass ball and try to make prediction.
Everybody else.
Yeah, I don't. Exactly. Personally, I don't think it will be an issue. Like everything is kind of on hold, and like there are all these like disturbances. But I don't think it will. Like personally, I don't think it will make such a big effect. Also, like postdoc situation is hard now. Like it's hard to get the position now, but once it's like everything like is kind of like over after 1 year, I think everything will go back to normal. Yeah, that's my personal prediction by like having like a feeling of United States. But yeah, it's yeah. And I have actually, this is the Cosmic Explorer T-shirt for the next generation detectors. So I'm hopeful for LIGO and for the next generation detectors. Yeah, and in October we'll be over with the observations, and we'll have a 2-year break to improve the detectors and go in the 5th observing run. That will be like 3 years, and it will be a very long run, and we'll have detection like basically every day. So it's like everybody is like preparing for that. The critical part of what we do is the low latency searches. If you detect a gravitational wave source that potentially have electromagnetic counterpart or neutrino counterpart, then we have this low latency, the real-time searches will let the astronomical community know that we detected something, just like look at this piece of the sky. And as I said, we had like 201 detections so far, so it's like we have like few of them a week. Here I also have like several different resources, so you can see the gravitational wave detector sensitivity in real time. And if you compare the detections that we have from the first observing run until now, it's like constant increase. So if you improve the sensitivity even a little bit, you are getting a larger volume where you search. So if you improve the sensitivity, say 2 times, then your volume enlarges to the third 8 times. So it's worth actually taking the detectors offline, make them more sensitive, and then start observing again. So you realize, as you can see, like the slopes of the rate of the detection is basically constantly increasing.
So the squeeze light is O3, yeah?
I think squeeze light was already in O2. I don't remember if this was O2 or O3. But yeah, like it's now it just used, the squeeze light is used as a regular component. Okay, and the third generation gravitational wave observatories. So we had Einstein Telescope collaboration meeting a few months ago, and the big news is that we don't know what will be the shape of gravitational wave detectors. Initially, the project initial was to have triangular detectors when you have 3 detectors creating a triangle, but now there's a lot of technical difficulties technical challenges. So people are thinking about the L shape, and now there's a lot of work toward understanding what should we do, either L shape or this triangular shape. And the location is like a big one. So up to now we had 2 sites when we have when we can host gravitational wave. When we can host Einstein Telescope, but now we have the third site, which is Saxony. It's basically like 30 kilometers from our Polish border. So this is like another site that is still going through like approvals and stuff. But yeah, like effectively we will have 3 possible locations when we can have Einstein Telescope. So yeah, do we build 1 Einstein Telescope? Do we build 2? These are all questions that are still very much undefined. So yeah, it's a very hot piece of equipment, and yeah, like many people would like to have it. And yeah,
is Poland taken into account as a possible place for LIGO kind of detector?
It was. So so initially there was like I think like 10 sites that they were measuring seismic noise, and yeah, in Poland it was like Katowice, but close to Katowice some mines, but yeah, at the moment yeah, only two sites were selected, like Sardinia and say like Maastricht in Netherlands, and now there's the third one. But yeah, like Poland. So actually, the Polish team was measuring all the seismic noises all across Europe. So that was actually a base for like doing the study where we can put it. So yeah, like Poland was one of the possible locations. Okay, and so let me explain what do I mean for exceptional gravitational wave sources. So as I said, if we have another binary black hole from stellar evolution, it's like yeah, another standard vanilla source. So we want to detect those gravitational waves that carry some unique information, something that hasn't been seen before. And if we have a new source population of gravitational waves, we have, say, binary black hole with eccentric orbit. So everything that we detected so far has basically circular orbit. So something that has eccentric orbit, maybe hyperbolic encounter when you have black hole, and then another black hole that is basically flying by, and that's also is emitting gravitational waves. Maybe we have 2 black hole colliding, some really extreme mass-ratio of like, say, 1 to 100. So you have black hole of 100 solar masses, and then maybe some like neutron star or some light objects of like 1 to solar masses. Also, if we have a non-binary source like core collapse supernova, and I will talk more later, the pulsar neutron star glitches. So if you have fastly rotating pulsar, when the crust basically is breaking on the surface, it is also emitting gravitational waves, and maybe eventually cosmic string. And also, I put in the basket of exceptional gravitational wave sources something that astronomers are basically like waiting like every day, is the multi-messenger sources. We had detected so far one binary neutron star, and then we have learned like tremendous amount of stuff about kilonovae, so what is the remnant of that collision. We haven't seen yet the multi-messenger signal from neutron star black hole, and we also want to probe what is happening right after the binary neutron star is colliding. So we can also like probe other phenomena. So you can, if you think about gravitational waves, they have like the main mode and then some higher harmonics, like similar to if you have a bell. You have like a central mode, and then you have like higher harmonics. So like a similar way that when you have black holes, like basically oscillations of the black holes. Gravitational waves carry two polarization, and we detected so far only one. We can have a detection of basically low frequency, the memory. So if a black hole is basically kicked out from the system, we hope to measure the signature of that. High precession or high spins of 1, 2, or final black hole. Hopefully we can see black hole creation at this very moment. Or if you have a black hole signal, you have basically length signal similar to what is in the electromagnetic spectrum. You have when gravitational wave will be passing through, like in front of like a galaxy, then you can have you can detect like two signals. So this is something that is like fairly promising in the next maybe like before the end of 05. And then we can test general relativity in many different ways. So there's a big zoo of like different possibilities, and it's not possible to model everything. And the tools that we are using is called coherent waveburst. This is a model-independent search that doesn't make any specific assumptions of the signal morphology. It can use some minimal assumptions, saying that let's look for the binary black holes and restrict our frequency range down to like 300, 400 hertz. And let's look for stuff that is like chirping. So this is, like we remove like everything else, but just have those signals that are chirping in time and frequency. And this algorithm detected basically the very first gravitational wave back in 2015. The first binary black hole was like 36 solar masses, like two black holes of like 30 solar masses, and much filtering. That is another technique that is like used like very widely. Was basically missed it because they were searching for black holes only up to like 15 solar masses. So this model-independent search discovered the first gravitational wave in real time. Discovered the intermediate mass black hole back 2019, and I had my involvement over here when I'm in charge of the low latency real-time analysis for this pipeline. We are detecting regularly gravitational wave sources, and we are contributing regularly to LEGO Viro Kaga papers. And I would say this is the most, if we have some an exploding star in our galaxy, this is the most sensitive algorithm to actually detect gravitational waves. And if we have a binary black hole from with eccentric orbits, we don't have models yet, like full models to do filtering. So also this algorithm is the first that has a chance to discover that. And how does it work? We basically do the analysis in time frequency domain. So you take your time series basically your x of t, the output from the detector. We decompose them into time frequency map. We add these maps together. This way, signal adds incoherently, and the signal adds coherently, and the noise adds incoherently. So effectively, you are enhancing the signal. And this is the example that I showed before of the binary black hole from the binary black hole system. Then you take these maps and you can analyze its properties. So that I will not go into the details of like how these maps are created, but it's like fairly complicated. The bottom line is that much filtering is filtering the data in time or frequency domain. We are doing the analysis in time frequency domain in this two-dimensional space. And we have different ranges of searches. So I mentioned that we can have minimally modeled searches for binary black hole. The frequency range is up to like 300 hertz, and we are looking for the chirping structure. Then on the other side, we have the generic searches. So we are looking for the signal up to like 2000 hertz, and we don't make any assumption of the signal model. And this is like one of the examples of such signals. And there is something in between. If we have eccentric binary, if we have head-on collision, or if we have intermediate mass black hole, this is roughly what we see, just basically like blob of energy. Only the merger part is visible. And
can I ask? You talked about this multi-messenger events. I understand that the key there is some kind of a window you need to have after you register with the gravitational wave that you can then target with the telescopes, right?
Yeah. So if we
what are the time scales? Is it because you said you do this in real time, and then within seconds you need to tell the guys in Chile or Hawaii to change the angles, or is it days, or is it?
It's basically a matter of like a seconds to a minute to send the information with the sky location. Like look at this part of the sky, like the first one, and it's they're basically taking the telescopes and just like go to that specific direction. And
point of view, what is the time window? Maximum time?
It depends on the source.
Far away, you have more time.
When it is far away. Usually the window it's set to say 30 seconds after the gravitational wave signal, and then 600 seconds before. So this is like the typical window when we have when we might have a coincidence for far sources. If we have supernova, then the neutrino detector will like pinpoint the time like pretty well. But in real time, it will be like 10 seconds coincidence. So the gravitational wave should be like within this 10 seconds. In general, it's like minutes. Look for the signal like minutes around that around the gravitational wave signal.
And this analysis takes seconds?
It's usually just takes seconds to have like the first alert. Like I would say like 30 seconds is like the ballpark. We have also so-called early warning alerts. So if you think about the binary neutron star, they're basically, these are pretty light system, and they are merging slowly. They start from the low frequency, and it's possible to get the gravitational wave signal, like the warning about the gravitational wave before it happens. So at the moment, for some strong signals, it can be like even like 30 seconds before the merger happens. So we have this infrastructure that we can send like rough sky localization to the astronomers before the merger actually happens. before the kilonova appears on the sky. Yeah. Okay, and maybe like very quickly, the intermediate mass black hole. If we have so something maybe that I would like you to also remember, the heavier binary, the lower frequency of gravitational waves. So this GW 150914, this black hole with the mass of final mass is 60 solar masses. But GW, this green 190521, is 150 solar masses. So this, the higher mass, the lower frequency. So if you want to detect very, very heavy binaries, say like 1,000 solar masses, we are limited by this low frequency noise, basically the ground vibration on the surface of the Earth. And yeah, like this, like 150, 200, maybe a little bit higher masses. They are at the edge of the capabilities of detecting binary black holes. And let me also quickly mention about the eccentric binaries. So we haven't detected yet binaries with eccentric orbits, and I would say these are very interesting events. So they have to happen in the so-called globular cluster with very dense environments when you have like a random encounter of two black holes. And they don't have enough time to actually create circular orbits. So from modeling the galaxies, modeling the universe, this is something that is very, very interesting. And the input for gravitational wave detectors from our observation is basically like one of the keys. And yeah, at the moment we don't have the models. It's really hard to actually model this type of binaries. So we made like studies comparing like different models, and yeah, above certain ellipticity, they start not agreeing. So yeah, this is like one of the areas that people are working like very, very intensely. Okay, and just quickly, so I mentioned about low latency searches, and in real time we have two types of searches. The one that is like the most generic, and the one that is tuned to detect binary black holes. But let me move on and say quickly. And I have a question. So how much time do I have?
So like maybe 10-15 minutes.
Okay, perfect. Yeah. And let me go to core collapse supernova. So this is something that I was working a lot. And if you look at the sky, when people were looking at the sky, they saw basically stars. But eventually, from time to time, you had like a star popping out on the sky that was like really, really bright, that was like visible even during the day. And like people were calling them new star, nova star. And 1,000 years ago, there was this supernova that happened in our galaxy, that was spotted, and it was like written as a guest star on the like Chinese scripture. And now we know this, like they didn't know, it's just like a guest star appeared on the sky, but we don't, but now after 1,000 years, after having telescopes, we are able to say that, oh, these are the exploding stars, massive stars. So how does it work? You have basically, you start with a star from a hydrogen, and the star basically is burning this hydrogen into helium. Then you have burning to higher elements up to iron, where the burning stops. So you have basically a star of an onion shape, and if that iron core that is in the center basically exceeds a Chandrasekhar mass, it basically collapses, and that triggers an explosion. And it happens that 99% of that energy basically escapes with neutrinos. So while we don't know what is the mechanism that drives the explosion, modeling is extremely hard. It's just, these are the most challenging sources to actually model. We think that the neutrinos are the prime sources of these explosions. Basically, you have like a very hot so-called proto-neutron star that basically boils the star from inside and basically just push matter outside. And we haven't detected gravitational waves so far. We need something that will explode in our galaxy, but gradually we are basically create upper limits on the emission of gravitational waves and slowly make constraints on the supernova engine. And yeah, it's basically done in the frequency domain. So like we say that, after collapse, you have like a cigarro that is created due to like huge rotation. And yeah, we are able to now constrain some of these models. Possibly we'll be able to constrain such scenarios coming from like numerical simulation, because like people also find this type of bar mods in the like bigger simulations. But then in order to get to more realistic ones, we have to really go down with the sensitivity and with we need to have something that is like close by. So yeah, we need something that explodes in our galaxy in order to realistically have a discovery of gravitational waves. And yeah, there's a lot of work on creating tools for understanding what's happening inside, but let me skip that. And let me just say that LIGO Virgo Kagra is pretty close in terms of, yeah, you practically have to either build a detector or analyze the data. But now, after recommendation from National Science Foundation that funds LIGO, they thought, okay, let's start off more discussions with the theory community. And the first source actually that you can think of, the most like interesting source, is basically core collapse supernova. So the next supernova in our galaxy will be basically one of the most important events of the century. Yeah, people want to get really, really ready for that and have like real discussions. So there was actually a few locations that wanted to host like joint meeting between the gravitational wave and theory community, but through a voting, like Warsaw was choosing, and I'm displeased to actually have this symposium here, basically in Warsaw, and it will be in this room in July, 21 to 25. Why is the 23? Yeah, 5 days, 21 to 23, and it will be right after, if you are familiar, in GR24 and Amaldi 16 meeting in Glasgow. So like when people come to Europe from overseas, they can quickly also jump to Warsaw for this symposium. And there will be a lot of discussion from the theory community, gravitational wave. We'll have lectures on, we have to get to understand each other. So it will be an important meeting. We'll have also like a paper coming out of that, and we have proceedings. So like everybody will be able to like contribute their work into this symposium. So yeah, that's happening in July. And a little bit of a quantum twist. So since this is like quantum colloquium. So one of the things that I'm interested in, and this field of black hole spectroscopy will be coming out basically really soon. So if we have strong signals, detected strong signals, we'll be able to measure how the black holes oscillate. And the math behind it is pretty complicated. And this mathematical formalism is basically very similar to is in quantum mechanics. So basically, you just have a black hole, you perturb it. We have basically also this higher harmonics from gravitational wave oscillations are also numbered by quantum numbers. So this is a very promising field when you can literally just measure black hole oscillations and basically test general relativity or maybe get an insight of really what are these objects. So that's something that I'm interested in to explore, which is mathematically very close to what we have in the quantum mechanics. And another thing that I discovered recently, so I don't know too much yet about that, but something that that I would like to explore is the atom interferometry. So for gravitational wave detectors on Earth, LIGO, we can go down to like 10 hertz. With the space-based detector, we can probe gravitational waves like below 0.1, 0.001. But there is this gap between space-based and Earth-based gravitational wave detectors, where people try to feel like in different ways. But one of the promising ways is to have atom interferometry, and it's basically you are basically dropping dropping atoms, and if they are interacting with if the gravitational wave is passing through, then you have a time difference for their arrivals. So this is something that I don't know much yet, but I would like to explore, and this is I think it's also like closely related to what you do. And let me finish saying that the gravitational wave astrophysics is promising. It's loud. We want to have discoveries. I work on the model independent searches. I'm organizing the symposium on core collapse supernovae between gravitational wave and theory community, and there are certain directions that I would like to explore. So I hope I'm on time, and thank you so much.
Okay, thank you very much. So we have questions. Yes, Krzysiek?
So these time frequency plots which you showed, how are they made? Are they made using wavelets, or they are made just by having a Fourier transform on a moving window?
So actually, I have like these slides. So this is how this is usually done when you have a short time Fourier transform. So if you do Fourier transform, you have to specify like your time window, and you just move it, and like each moment of time, you basically probe the frequency, but you get like so much different way. Like you can see the signal in many different ways depending on that window duration, and you can probe like short signals when you have like a short window, and long signals when you have long window. So there's no like clear solution to that. You have to do so. Let's say you have all these like different representations of the data, and then you combine them into one. And I don't want to go into the details, but you have this.
So you combine the results with different window size.
Correct. But you have to be very careful because you can have a lot of say. Oh no, you can have this energy leakage in frequency and in time. So you have to design your transform in order to be as to have as little this energy leakage as possible. You want to know exactly what is the energy in that particular point.
And this window, is it rectangular or it's something?
It really depends. So it's basically an experimental work to basically see which type of window gives the best properties. And also, if you have like this type of time frequency maps, unfortunately, there is no transform back to reconstruct the signal in time domain or in frequency domain. This is like highly like oversampled, and mathematically there is no it's not possible. So yeah, the transform that we are using is called WaveScan, and yeah, it's like special transform that has all these properties of combining these maps, and then you can go back to to see how the signal looks, and you are minimizing this energy leakage in time frequency. Plus, you can also shift nicely data, so you can get the sky location. So there's a lot of different properties that you have to fulfill. So it's actually this is actually not trivial.
Mm-hmm. Michał?
Hmm?
Yes. So I have a question. So people in quantum science like to now build setups that are super sensitive at super high frequencies, because there is obviously way less noise at high frequencies. So I don't know, for example, quantum mechanics, quantum mechanics, you have essentially probe masses that are super sensitive, but at very high frequencies. Is it realistic to find, because they like to brag about that they may detect gravitational waves. So I want to ask, is it realistic to look for sources at megahertz to even gigahertz frequencies, even higher than you've shown in this atom interferometric?
Yeah. So. Yeah, definitely. This field actually gains attention, and I saw recently like white papers that, with like tons of authors, that they try to like get this field together and really look like increase the sensitivity of like megahertz. So hopefully, but if I think about physics, basically, if you have in order to generate gravitational waves, you need to have basically certain oscillations, say, of matter. Like, how is possible to have like high amplitude oscillations at this like megahertz scale? Yeah, there are like sources, like in the cosmological sources that can generate such high frequencies. So it's something that I haven't yet explored, but I know that yeah, like the interest is growing. So that's basically what I could say.
Mm-hmm. Okay. Yes.
Can I have a super naive question?
Mm-hmm.
So, you know, those events, 300, so, you know, colossal kind of events somewhere far away from us. If asteroid will crash in the surface of the moon, are we going to see it by like?
No, it's like too little. No.
This is too small of an event.
Yeah, like I haven't made the calculations, but my intuition is saying like no, because mainly gravitational waves are coming from dense matter, and like matter that is like.
We are gaining of 1 over r squared.
Actually, the gravitational waves are going like 1 over r.
1 over r.
Yeah, like because we are measuring the strain, not the energy. But still, if you think about like white dwarfs that are like pretty dense, yeah, they are not. Yeah, the emission is more in the low frequency part, and yeah, like to have like detectable gravitational waves, you need to have something say like nuclear densities, something there, and like moon is still something that is it's very it's not dense enough. Even if you have a asteroid going like almost like at the speed of light, it basically go through Earth through the moon like through a fluid. So yeah, like I don't think it will be possible even if this is that close. But yeah, that's something that yeah, like I haven't seen anybody considering that.
Okay, I'm not sure. I'm not an expert, but I have a feeling that this kind of event is very different from like periodic signals. Yes? I mean, here, the main advantage in the signal, I think, is that it's kind of lasting for some time with some period, and that's why you can filter out it with this Fourier. I mean, if you have an event that's instantaneous, you basically have no frequency features. Yes, it's like a broad frequency event, and I think it will be very difficult to see this if there is no specific frequency in the signal. I think that's
some kind of modes of vibrations of the moon.
okay. If this was the case, then
yeah. So actually, if you think about say cosmic strings, it's basically like similar thing that you have like just straight up and down, or yeah, even for the if you have a head-on collision, it will be like something similar. So yeah, like. You cannot like filter that, but you can look basically at time frequency and look at the basically energy. But yeah, that would be a question. Yeah, would it produce undetectable gravitational waves?
Janek, yes.
Any hope for something beyond standard model? You mentioned cosmic strings. Any sources, maybe this megahertz, gigahertz. Is this community even having hope to see something beyond standard? What the high energy physics cannot do?
I know that they want to, there are proposals of using gravitational wave detectors to probe beyond standard model, but I'm not familiar with that. In general, there are not much discussions about that. It's practically, yeah, if you detect dark matter, so like you are probing the universe with black holes, you basically map the universe with black hole collision and then map it with yeah, gravitational wave detections. But yeah, that's the closest I could think, like looking for the dark matter, dark energy. But yeah. Yeah, so like in terms of like detection, people don't talk about much like within like my facility, but I know that there are papers and there works on that. Yeah.
So, any other questions?
Oh, maybe I can also mention something that is getting like more attention is like looking for gravitons. So maybe that's something that also would be like close.
By the way, to make this connection with this time frequency analysis, we in physics have such tools to analyze like position momentum simultaneously. It's called Wigner function, yes, and you can do the same for frequency and time. I remember we once with Konrad Banaszek we tried to analyze some signals with Wigner function, like with time frequency signals. It didn't work very well, but I was wondering if it at all makes sense to do it here, because it's in principle it's kind of similar idea, like you have these things that in principle cannot be simultaneously measured, but
The time is even related to the short time Fourier.
yes, yeah, it is related, but not, I think, not in a very obvious way, no?
There is a
Well, there's this time window here.
Yeah, in Wigner function you don't have time window, you just have
Time window is key here. It's really...
Yeah, I know, but in Wigner function it's like time window is like instantaneous, it's infinitesimally short time window in some sense, yes?
We want to filter all the noise. So in Wigner function we have one quantum noise, which is light, and we know what to do. Because here you guys have all different type of noises, all different type of filtering.
No, but you still have the same, you can plot it like this. Yeah, and then these features should be there, no?
Oh,
At
but
least some features should be there, okay.
Yeah, because like it's even called high-spread rule for signal processing, and that's one of the big limitations we have. So No, that would be at least maybe like worth trying.
Okay.
Yeah.
Okay. Yes, I think that's it. So let's thank the speaker again.
Thank you.